Good morning from Dhaka, Bangladesh. This is the 11th lecture on chemical bonding and structure of the series of AS and A-level chemistry. We'll talk about polarity of molecules in this slide. See, covalent bond is formed by sharing of electrons by two atoms. And this covalent bond can have two types of covalent bond. One is called polar covalent bond and non-polar covalent. Non-polar covalent, for example, hydrogen molecule, chlorine molecule, bromine molecule. We have to notice that this hydrogen molecule, when two hydrogen atoms are forming bond, their electronegativity values are same. Therefore, covalent bonding in hydrogen molecule, chlorine molecule, and bromine molecules are called non-polar covalent bonds. But then we come to, if there are atoms having different electronegativity values, then we form polar covalent bonds. What happens? As a result of sharing of electrons, the electron distribution becomes asymmetric in the two atoms, and partially charged developed, and one becomes delta positive and another becomes delta negative. And here is an example of polar covalent bond, hydrogen chloride. You see, hydrogen has got low electronegativity than that of chlorine. Therefore, a charge developed here on chlorine is negative, and the charge developed at hydrogen is positive. And we show this like an arrow here. The arrow heading is towards more electronegative atoms. Okay, then we have this polarity we can also measure by dipole moment. And the values of dipole moments we can spectroscopically determine. Dipole moment spectroscopically determined. And we can see that in molecule also, though there are polar covalent bond, but in some cases, the dipole moment cancel each other of the polar covalent bond. For example, here, tetrachloromethane. We have polar covalent bond, this one, this one, this one, this one. But then overall dipole moment of this molecule is 0. Therefore, tetrachloromethane is a non-polar molecule. However, trichloromethane, here we developed a dipole moment for this polar covalent bond, this polar covalent bond, this polar covalent bond, and this polar covalent bond. And there we developed a charge, a positive charge and negative charge. Therefore, we call this non-polar covalent molecule, polar covalent. Okay, we go to next slide. This one, I show you the covalent bonding and as well as ionic bonding. You see, when two atoms have electronegativity 0, it forms a covalent bond, but this is electron shares between the atoms, and the nuclei of these two atoms equally attract the bonding pair. And therefore, we call this one as a non-polar covalent. This one is as a polar covalent. And this magnesium iodide, which is an ionic bond, but since there are some electronegativity difference, but it is not as high as this one. So therefore, we have a covalency also, little bit partial covalency in this ionic bond compound. But here, sodium chloride has got a high electronegative difference value, and therefore this is a purely ionic bond. So we are talking about now the properties of simple molecular substance having covalent bond. What is? In general, this covalent bond has got solids, gaseous state, liquid state, or soft solids at room temperature in general, but there are some exceptions too. Have relatively high, low melting point and boiling point. Do not conduct electricity. Are soluble in non-polar solvents such as hexane, then in water, and the solution in hexane do not conduct electricity. This is the very general properties of covalent bonds. Now we are talking about a very interesting substance, metals. Metals are very, very useful and important substance. We know, all of us know that. How bond forms in metals, that's what we have to think a little bit. First, we think about how structure is being developed for these metal substances. And we can study the structure by X-ray and find out. In almost all cases, the metal atoms are packed together as closely as possible. And this is called close packing. What is it? A model of few atoms in one layer of metal crystals is shown here. Look, this one, this metal atom has got 6 neighboring metal atoms. And you can see that there are some holes here. Is not the second layer of the metal atom in 3 dimension, if you think, that fits in the hole of this one. So the third layer, when we talk about, is if the third layer is exactly like first layer, we call the close packing hexagonal close packing. That means in 3 dimension arrangement is like this. If A is the first layer, B is the second layer, then AB, 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 etc. We have another close packing, which we call cubic close packing. In this case, we have the first layer, then we have a second layer. If we call this A, first layer, B is the second layer. And then we see that third layer is different from A and B. But fourth layer, again, it's exactly identical with A, and fifth layer B, and sixth layer C. And these continues 3-dimensionally. And we call it cubic close packing. The structure is very important to know about the metallic bond. Yes, as we said, like this, we have close packing and we call it a giant lattice of close packed atoms in a regular pattern. But the electron in the outer shell of the metals, are not fixed in a fixed position. They are delocalized electrons. So metallic bond consists of a positive ions of metals and electrons moving around and between them as a sea of delocalized electronegativity. These are electron, sea of delocalized electron, these are electrons, these are electrons. And therefore, we have a strong force between the metal atoms, and we call that metallic bond. Now we go for the very important properties of metallic bond. How metallic bonding increases. We have increasing positive charge. When we have increasing positive charge in metal lattice, if we're decreasing size of metal ions in metal lattice, and increasing number of mobile electrons per atom, that gives the increasing strength of the metallic bond. Properties of metals, as we discussed, all properties of metals can be explained and interpreted in terms of close packing structure and delocalized electrons. However, in some general properties of metals have high melting point and boiling points, have high densities, are good conductors of heat and electricity, and they are malleable. And what it means malleable? That you can hammer it and make it a different shapes of the metals. Well, then we have to talk about a little bit about intramolecular forces and intermolecular forces. You know, when atoms having attraction in the molecule, we call that force intramolecular forces, which are relatively strong. But we do have another force between two molecules, not in one molecule, and that we call intermolecular forces. Interesting thing is that if we do not have intramolecular forces, let's say we are not having intramolecular forces in chemistry, what would happen then? We would not get rivers, we would not get oceans, we would not get even DNA. So in water, DNA, we do have intermolecular forces. And Dutch physicist John van der Waals, he developed the theory of intramolecular forces to explain behavior of real gases. So what has happened? If there were no intramolecular forces between molecules, it would be impossible to turn a gas into a liquid by cooling. So let's see how important is intramolecular forces. So the following are the different types of intramolecular forces. One is instantaneous dipole and induced dipole forces, which is also called London forces, as German physicist Fritz London developed a theory to explain these forces. We have also permanent dipole and permanent dipole forces, which is also intermolecular forces. We have hydrogen bonding, which is a strong form of permanent dipole and permanent dipole forces. The following three van der Waals forces we talked about, and if different types of chemical bonding and different forces are understood, this will help us to explain structure and some physical properties of elements and compounds. I have just shown this instantaneous dipole and dipole induced dipole forces, how it occur. You see that these two as non-polar molecules. But when they meet, they just have a instantaneous repulsion or attraction, and thereby having this sort of charges developing, and that which is called weak short-lived attraction between temporary dipoles. We now got permanent dipoles, and you see this. If you look to this, then you can see this is a repulsion, because here is delta positive and there delta positive, so it will have a repulsion. But here that will have a attraction. Is it not? The negative and delta positive. And this is the way we explain the permanent dipole and permanent dipole forces. And we have weak permanent dipole and dipole forces. Here you can see this is the organic compounds, and we have developed here a positive charge, and as oxygen is highly electronegative, therefore we have developed a negative charge here. We can take an example, propanol, whose relative molecular weight is 58, has a higher boiling point than butanol, which has got a relative molecular weight 58. This means that the more energy is needed to break the intermolecular forces between propanol molecules, but between butane molecules. We don't have a permanent dipole forces here. We are talking about intermolecular forces, and the third one is hydrogen bond, which is the strongest form of the intermolecular forces. How it happens? Two conditions we have to have. One is the covalently bonded molecule must have a hydrogen atom. Okay? And then it must have also a highly electronegative atom. The highly electronegative atoms are nitrogen, oxygen, and fluorine. You see? Then, if we talk about this one, this is a water molecules. And if this is also another water molecules, you see, this one is highly electronegative, and therefore there is a strong attraction between this highly positive hydrogen. So therefore, we develop a hydrogen bond in water molecules or hydrogen. Similarly, we show here the way of hydrogen bonding in covalent. This one is covalent bond, but this oxygen will have an hydrogen for this oxygen, and this hydrogen and this oxygen is also hydrogen bonding. Hydrogen bonding has got some properties which is very different from others. Let's talk about halogen halides. Halides. That is hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. And the boiling point, we see only hydrogen fluoride has got hydrogen bonding. Hydrogen chloride, hydrogen bromide, hydrogen iodide do not have hydrogen bonding. Why? In hydrogen fluoride, fluorine is highly electronegative. And you can see the boiling point, which decreases like this. And then when it is a molecule having hydrogen bond, the boiling point sharply rises. And this is a properties of compounds having hydrogen bond, that they will have different types of properties than that of their group compounds. Similarly, we are showing here boiling temperature in Kelvin. Here is in Celsius in Kelvin. The group period, you can see that water has got hydrogen bonding, but hydrogen sulfide, hydrogen selenide, hydrogen telluride, they do not have hydrogen bonding. Therefore, there you can see the sharp rise in boiling point. We go for the next slide. Well, we are talking about bond length and bond strength now. What is bond length? Bond length is nothing but the distance between nuclei of two bonded atoms in a molecules. Bond energy is particularly bond energy, the energy required to break one mode of the bonds in a substance in the gaseous state. These molecules in solid state can be, as I said, can be studied at X-ray diffraction and get three-dimensional structure. And from there, we can get the bond lengths and bond angles. A bond angle is the angle between atoms forming bonds in a molecule and compounds. We also can get bond lengths by spectroscopic studies. I have shown here a series of compounds having halides. You see. The bond length between this one, hydrogen and fluoride, is 0.092 nanometer. You can see bond length here is 0.127 nanometer. And here you can see bond energy. The smaller the bond length, the higher is the bond energy. Because if it is smaller bond length, the molecule atoms are bonded very tightly, and therefore it needs higher energy to break the bond energy. And here I take another family, carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond, and you see the bond length decreases, and thereby the bond energy also increases. Well, we have been discussing about bonding in molecules, but then we are also to talk about structure, or even in some cases shapes of molecules. You see, structure and shapes are completely different things. Shapes, it is not a three-dimensional one, just a model, but a structure in three-dimensional says about how the atoms are arranged regularly and the atomic position, etc. Here, what we will do, we will take the bond pair and lone pair of the central atom and predict about the shape of the molecule. And that what is called valence shell electron pair repulsion theory. In short, VSEPR theory. Okay, we know that electrons having negative charge and they will repel each other when we arrange them. So, due to this repulsion forces, pair of electrons apart until the repulsive forces are minimized. The shape and bonds angle of covalent bonded molecules depends on the number of pair of electrons around the central atom. This is very important. And whether there are lone pairs and bond pairs, that also dictate to talk about the shape of molecules. And as I said, repulsive forces has to be minimized in 3 dimensions to get the shape. So valence shell electron pair repulsion theory says lone pair will have highest repulsion, and lone pair bond pair lower than that, and bond pair with least repulsion. So with this, we can see the shapes of molecules. Behind this, we have to find out the bond pair and lone pair of the central atom of a molecule, and then say about how the shape of the molecule will be. In the next lecture, we talk about the shape of molecules and from different angles and the shapes, and then we will also find out the bond length and bond angle of those shapes we will talk about. Thank you very much. We take in details the shape of molecules in the next lecture, that is 12th lecture of the 6th.